Hello guys, this is the second video, part 2 of chapter 23. How to tell if the population is evolving. Before we start, we're going to go through two vocabulary words. One is population genetics. So study of how population change genetically over time. So we just need to know whether the overall genetics within the population is changing or if it's modifying within or if anything are expressed more or less. So that population genetics. Second one, population in general. Groups of individuals that live in the same area and interbreed, producing fertile offsprings. So basically, this is already stuff that we know from previous chapter. So these two keywords that we need to know for this part of chapter 23. Okay. Furthermore, within the population, we need to know something about them. Well, gene pool is an expression of all the alleles for all the genes in all the members of the population. So, as using human as a example, we are what we call a diploid species. So that means we have two alleles for a gene. Okay, so it will either be because we have the two alleles, we will have either two options: homozygous or heterozygous. That means homozygous means the two alleles are exactly the same. Heterozygous means the two alleles are sort of different. Okay, and because we have two alleles, there's actually a lot of different combination of possibility that we can have because we have two. Some of the other animal organism in general, have what we call haploid, but later on we'll talk about it when we talk about genetics a little bit more. Okay, another thing is fixed allele. Fixed allele means all members of a population only have one allele for a particular trait. So this is a very unique situation where every single person, let's imagine every single person all have this specific allele within our genetics information. So what that means is the more fixed alleles we have in a population, the lower the species diversity will become. That means whenever you have one allele that's fixed, imagine it's frozen, we cannot change it, there's no other options, then that single allele is going to cause the overall diversity to decrease because there's not much diversity within that allele. Okay, and that makes sense because when we freeze that one options, you just have to choose it. There's no other option to choose it. Okay. Next thing, we talk about it's going to be Hardy-Weinberg theorem. Okay. Basically, this is how we know that allele and genetic frequency of a population will remain constant from generation to generation. Okay, basically that's what they're saying. That's their hypothesis. That's their theorem. Unless they're acted upon by forces. Okay, so unless other factors, otherwise, the frequency, the genetic frequency, genotype, and an allele would be the same. Okay, but there's exception. Other than Mendelian segregation and recombination of alleles. Okay, so just keep in mind the theorem has its limitation. Okay. And furthermore, Hardy-Weinberg come up with this equilibrium condition within a population. So what happened is when the population achieve equilibrium, the alleles and the genotype frequencies will remain constant. Okay, just like the theorem that they proposed. Okay, so in order for the allele and genotype frequencies to be constant within a population, the population has to be, in their words, reach equilibrium. So equilibrium is the key word that we know that the population and genotype frequency will be constant. So the condition for the Hardy-Weinberg equilibrium to be achieved are the following. Number one, there will be no mutations within population. 2, there will be random mating. 3, there will be no natural selection. 4, extremely large population size. 5, there will be no gene flow. Okay, and if at least one of these conditions is not met, then the population would be considered as evolving. Okay, so all five conditions has to be met before we can consider this population has reached Hardy-Weinberg equilibrium. Okay, going back to number 5 really quick. No gene flow, just to kind of go over what it means. It basically is talking about there will be no like outside forces to modify the genetic information. So that's a key one. So if you can see everything from these 5 conditions, we're talking about a pretty confined, well, not confined, confined is not the word I'm looking for, but a population that stays within its mean. Let's say it's almost like a population has built a castle and they just stay inside and everything happens inside. So these are the conditions of Hardy-Weinberg equilibrium. So these are the mathematic end of Hardy-Weinberg's principle. So allele frequency, genes with 2 alleles, we have a P and a Q to represent either dominant allele, like this, or recessive allele, like that. And furthermore, we also use capital A and lowercase a to differentiate between dominant allele and recessive allele, respectively. Okay, so because it's equilibrium, we will have a mathematical equation that's represented like this. P plus Q equals 1. So the frequency of dominant allele plus the frequency of recessive allele would eventually equal to 1. Okay, and we know if that's true, then for some of you who are very good at math and love math, then we can also derive the other 2 equations. When we subtract dominant alleles or the recessive allele, the frequency of them, from 1 we'll get Q and P respectively. Okay, so that also makes sense algebraically. Second thing that we know is if we want to find out the genotype frequency by using these 2, P and Q, we also can find out the 3 different genotypes that we have. According to earlier, we will have big A, big capital A, big capital A, which is talking about homozygous dominant, big capital A and lowercase a, which is talking about heterozygous, and then finally lowercase a, which is talking about homozygous recessive. Okay, and because they're expressing the specific dominant gene or recessive gene, so we can also categorize them as P squared because there would be 2 dominant allele, and then 2PQ, which because we will have a heterozygous genotype, and then Q squared because we will have homozygous recessive. So because we are in this environment, and early on we said that P plus Q equals 0, well, the expression of these genotype frequencies will also equal to 0 because we're in an equilibrium, because we're not changing anything. So therefore, P squared plus 2PQ plus Q squared will equal to 0. Okay, an example of that, I'm talking about allele frequencies. So let's say we have different flowers, okay, and then the parent generation, we have these flower, okay, and then so from the parent generation we can see that 80% of the time will produce red flower, and 20% of the time will produce white flower. So that's what we were given. Okay, so we also have the frequency right here. P equals to 0.8 because 80% of the time, and Q equals 0.2, so recessive and dominant. And then from the mother side, also this within this population, because it's within the same population, we have 80% of the time we'll have red flowers, and then 20% of the time we'll have white flowers. Okay, as they mate and produce offspring, we have this new combination, again, this new frequency. From their offsprings, we found out that 64% of them would have red flower, okay, and 32% of the time we'll have pink flower, and eventually at a very low percentage in compared to everything else, at 4% of the time we'll have white flower. Okay. And this is kind of talking about different genetics combination, and this one kind of talks about how we calculate the different frequency of genetic frequency. Okay, and earlier this one is allele frequency, and this one will be genetic frequency, which gives us the different combination, different possibility down here, which is what I just talked about. Okay, so the strategy for solving Hardy-Weinberg problems are the following. One, if you're given the genotype, the capital A, lowercase a, lowercase a, we can calculate the P and Q by adding up the total numbers of A and total number of lowercase a alleles. Okay, so if you're given genotype, you can just find P and Q by adding up all the numbers of all the A and A alleles. One's capital, the one's lowercase. Two, if you know the phenotype, then we can use the lowercase aa to find the q square. And after we find the q, after we find the q square, then we can find the q. And when we find the q, we will be able to find p using this equation that we have right here. And three, to find out if a population is evolving, we can just calculate p squared plus 2pq plus q squared. And if that equals to 1, right here, then we can say that the population is indeed in the equilibrium situation. But if it's not, then we can say the population is evolving. Okay, so keep in mind, when p squared plus 2pq plus q squared equals 1, then the whole population's in equilibrium. If it doesn't, then it's what we call evolving population. Okay, now let's do an example question. I know I gave you 2, but let me do 1 and we'll do more in class as well. So the scarlet tiger moth has the following genotype, and we need to calculate the allele and genotype frequency percentage for a population of 1,612 moths. Okay, so the AA frequency and the big A, small a frequency and the 2 small a frequencies are given to us. Okay, let's calculate the genotype frequency first, because all these are given to us because, well, we have AA and AA and OA. So how we do that is we're going to take the number that they gave us from the entire population and divide it by overall population size, which will be 1612. And from that, I can get, let me do a quick calculation, which would be 0.911. Let me do 3 decimal, 0.911. Okay, and the same thing I'm gonna find using 138 divided by 1612, which I will get I will get 0.08 0.085. Let's just say 6, rounding. And then lastly, I will use 5 divided by 1612 equals to a very small number of 0.003. 0.003. Okay, so now we have found our genotypical frequencies just by dividing each one of them with our total number.